Okay, so today we're going to cover a very fundamental and interesting concept in machine learning that is called kernel. And the idea is to change the representation of the data in such a way that separation becomes possible, or classification becomes possible. So with a set of limited hypothesis set. Okay, so as we talked about many times in track learning, limiting the learning to a set of a hypothesis, a possible hypothesis, actually enables you to infuse knowledge, and also helps in preventing overfit. So let's look at this drawing here on the right, top right. So you have different points on the line. The classes is say class that is labeled 1, and the minuses is the class that is labeled -1. And clearly, if you look at these points on the line, you can't separate them into two groups, one the minuses and the other the pluses, using just a single threshold, which is equivalent in one dimension to a hyperplane. In one dimension is a single threshold. So you can't successfully separate the pluses and the minuses using a threshold of saying if x is less than 3, then it's minus. If x is bigger than 3, then it's plus. Because wherever you put this threshold, you'll have two sets, and two sets will have some mixture of pluses and minuses on one of the sides. So basically, the example on the left is not separable using a hyperplane. Okay. Now I use an embedding, and I change x to a x square. Now I get, I'm like pushing the points, and you get a parabola of the points. Now the minuses are lower than the line that I drawn, and the pluses are higher. So now I get a separation. So basically, that's the idea of the embedding and when you do this, you may run into computation challenges because, like for instance, I take say 2 point. I take a point in R6 and I transfer it to polynomials of degree 10. Then the space becomes the dimension of the space becomes much bigger, and that can lead to potentially to computational problems. So the idea of embedding points into a higher dimension in order to enable classification goes hand in hand in a way to compute it without explicitly computing in the high dimensional space. And that's the idea of the kernel that I want to cover today, how to do that. Any questions or comments up to now? Okay. So the key idea is to to get to a point where we actually don't need to explicitly calculate the scalar multiplication in a high-dimensional Euclidean space. So say we've embedded the points in R. Here we've embedded the points in R2. Say we've embedded the points in R 10,000. We don't need to calculate the scalar multiplication explicitly in R 10,000. Instead, there's some other function that is called the kernel that let us calculate the scalar multiplication in an efficient way that is not explicit. And typically we need to do that only for the points in the data set that we use for training. So we get the benefit of separation, but we don't explicitly do the calculation in R2, which in general could be a very high dimension. That's the objective. Any questions about this? Guy, is it clear?
Yes, I think so.
Great. Eliran, clear? Up to now? I couldn't hear you, Eliran. You need to go on mute. Okay, maybe Eliran has a problem with the connectivity. Okay, so yeah, so go ahead, Eliran.
Now you hear me?
Yeah, I can hear you now.
No, I was not on mute. It was something in my microphone. No, it is okay. Thanks.
Okay, great. Okay, so let's see two things. This is the crucial thing I want to cover today. Two things now. One is I want to show you a very simple example of kernel to make things concrete, and then I want to explain or give an intuition why you could expect that in many of the machine learning algorithms you can just calculate using the kernel of the pairs of data points in the data set, and avoid calculating explicitly the scalar multiplication in the embedded space. So consider the following kernel, which I want to explain why it's a kernel. But I have 2 points in R, and what I do is I multiply them and take the power, add 1 and take the power of 2. So this is a special case of taking the scalar multiplication of x and x prime in any dimension Rd, and taking the power of k, any k. Okay? And I claim that this is a kernel. So what I need to see is that I have some embedding in some higher dimension in which this is the result of the scalar multiplication of the embedding of x and x prime. Okay? So in order to see that that's actually the case, I just open parentheses, and what you see is that you get this result, because either you choose x prime on both sides, or you choose x and x prime and 1, or or x and x prime and 1, or you could choose 1 and 1. So basically that's the result you're going to get. And you see that this can be thought of as a scalar multiplication of the following embedding. So you have two vectors. One is 1x squared, and the other is 1x prime squared. And the scalar multiplication of both of them gives you exactly this. So you see that this embedding, taking x to 1x squared, give me exactly this formula. So the scalar multiplication of the embedding is the kernel function. Now, in general, the kernel function I can calculate quickly, because calculating the scalar multiplication of the two vectors would take me d operations if x is in Rd, and then I have a number, and I have to take it to the power of k. So it's just how much time it takes me to take any number in R and calculate the power of k of that number. So the computation is efficient. I don't need to explicitly embed it in the higher dimensional space. And I need to explain why it's useful. But the gist of the idea is that it's enough to know the scalar multiplications in order to calculate a lot of the machine learning algorithms, techniques we use. Okay, that's the gist of the idea. So you can see different machine learning techniques with the heading, for instance, SVM kernel, and so on. So basically, what they're saying there is that they have a way to calculate the SVM in a higher dimension using the scalar multiplication. They don't need to go to the higher dimension. So let's see an example, a very simple example, why this is the case, why the scalar multiplication may be enough. So if you look at the just standard regression, you see that I need to, if I have m points in my data set, what I need to do is minimize the following loss function, which is I take the scalar multiplication. W is the coefficients I'm trying to find so that this entire sum is minimal. And I'm basically taking the scalar multiplication of the W and Xi or Xj, Xi, doesn't matter. No, it's Xi. And then I subtract Yi and I take the square. This is the error that I have for each point in the data set, and I take the sum and I want to minimize that. This is standard regression. Now, in order to find the critical point in which you get a minimum, you need to take the partial derivative according to Wi. So you get m equations, which is 2 times this times xi, because here you have a sum of xi wi, and when you take the derivative according to wi, everything is 0 except the wi, which has the coefficient xi, so you get an xi here. So the critical condition sufficient conditions are that this is 0. Now this is a linear equation that can be solved by basically calculating an inverse matrix, and all you need to do in order to solve it is scalar multiplication. And you can just go over the Gaussian process again, or think about, assume that the matrix is inversible, see how you solve this, and you'll see immediately that you can just solve it using the scalar multiplications, and that's why it's enough to know scalar multiplications in order to solve the regression. So here we see that in order to calculate regression in an embedded space, with a kernel, we only need scalar multiplication. We only need the kernel values of the scalar multiplication of the different points. So that's the idea. Any questions or comments on this?
No.
Okay.
None from me either.
Okay. Okay, great. So thank you for joining today, and we'll speak next week.
Thank you very much, Eitan.
You're welcome.
Thanks, Eitan.
Thank you.